Next, we apply the conclusions of the previous theorem regarding the limits of power functions to the computation of the limits at infinity of a rational function. So what's a rational function? It's just a polynomial over another polynomial. So the theorem is about limits. It's about limit at infinity of rational functions. So we'll see shortly. This theorem actually applies. Well, the ideas behind the proof of this theorem also apply to more general expressions, not only rational functions. That's the last thing we'll do for this section. So the asymptotic behavior of a rational function depends only on the leading terms of its numerator and denominator. So this is the actual principle, and this is why we can apply the same thing to other functions that may not be rational. So how does it work? So if an, bm are both different from 0, then we have that the limit x approaches plus or minus infinity of an to the xn plus an minus 1 times x to the n minus 1 plus some other terms to a naught divided by b sub m x to the m plus b sub m minus 1 times x to the m minus 1 plus etc. b naught is equal to, as we said, everything depends only on the leading terms. So what are the higher powers here? X to the n and x to the m in the numerator and the denominator. So the leading coefficients are an and b sub m. And so what we're basically doing is extracting, going to factoring out by these leading coefficients, and now we are left with the limit as x goes to plus or minus infinity of x to the n minus m. And we already have a rule for the limit of a power function, was our previous theorem. So so you already see that if n is equal to m, then the limit will just be equal to a sub n over b sub n, because n and m are equal, so a sub n over bm. Otherwise, if m is bigger than n, then that is going to 0, because you have a negative power of x, and you're sending x to either plus or minus infinity, and you get the idea. So if instead n is bigger than m, as you send x to plus infinity, then this increases without bound. So, but then the sign of whether to determine whether that goes to plus or minus infinity will depend on the sign of an and bm. So that's the whole principle behind it. So how? Let's look at an example to see, to get an idea of what we're doing. Let's compute the limit as x approaches plus infinity of 3x to the fourth plus x cubed minus x squared plus 7, all of that divided by 11x to the fourth minus 2x squared plus 10. And this is indeed a rational expression. So here, well, we're asked to find this limit. What we know is, so for the solution, we don't actually need to go over this every time we're solving this kind of problem, but n here, which is the degree of the polynomial on top, so the numerator is equal to 4, m is equal to 4 as well, and a sub 4 is equal to 3, a sub 3 is equal to 1, a sub 2 is equal to minus 1, a sub 1 is equal to, and here there are no x terms, so this is equal to 0, and a naught is equal to 7. Okay, so similarly, b4 is equal to 11, b3 is equal to 0, b2 is equal to minus 2, and b1 is equal to 0, and b0 is equal to 10. Okay. Okay, so what does the theorem tell us? That this limit should be equal to, and we just care about actually a4 and b4, so it should be equal to 3 over 11 times the limit of x to the fourth minus 4 as x goes to infinity. But x to the 4 minus 4 is x to the 0, which is equal to 1, and the limit of 1 is just 1, so the limit 1 as x approaches infinity, which is just 3 over 11 times 1, which is 3 over 11. So this is the way this works. If you want to know why, find out why this works this way, we can look at the same example, and instead of appealing to the theorem, we can try to do it by hand. So we notice here that we have, well, 3x to the fourth plus x cubed minus x squared plus 7, all of that divided by 11x fourth minus 2x squared plus 10. So what do? We take out a factor of x to the fourth, 3, so this becomes 3, plus x cubed divided by x to the fourth, so it's 1 over x, minus 1 over x squared, plus 7 divided by x to the fourth. If you bring the x to the fourth inside, this is what you will get. So 3 times x to the fourth, plus 1 over x times x to the fourth, which is x cubed, which is the second term, then x to the fourth divided by 1 by x squared times minus 1, which is minus x squared, and x to the fourth times 7 over x to the fourth, which is just 7. We'll do the same thing with the denominator, and we get x to the fourth. The denominator is equal to 11 minus 2 over x squared plus 10 over x to the 4th. Here we can cancel out x to the 4th and x to the 4th because we're actually letting x become very large, and in particular is not 0. And what happens with the numerator? Let's look at each one of these terms. And we'll see that, except for the first one, they all go to 0 in the limit x goes to plus infinity. So 3 is just 3. When x becomes very large, this goes to 0, right? Because you're dividing by something very large. The same is true for 1 over x squared, and the same is true for 7 over x to the 4th. In the bottom, this goes to 0 as well. You're dividing 2 by something very large, and 10 over x to the 4th is going to 0 as well. You're dividing 10 by something that is becoming very, very large. So in the end, this whole thing goes to, well, what does the numerator go to? 3, and the bottom goes to 11 as x goes to infinity. Okay, so this is the idea behind the method to apply. So next video we'll go over another example, and then we'll apply the same principle to some other functions that, some other expressions that may not correspond to rational functions.